All right. Good morning. You all made it. We're continuing on with our multi-wavelength investigation of the ISM, moving to radio wavelengths today. Your lecture this morning by Andrea Bracco. So take it away.
Thanks. Thank you. Hi, everybody, and good morning. Thanks coming that early. So today I will keep on discussing with you some possibility to probe the ISM at different frequencies. Particularly, I was asked to introduce how the radio wavelength can contribute to study the ISM. I'm Andrea Bracco. I'm postdoc at INA Farcetri in Florence. And I'm also a project scientist for the SKA Regional Center Network that I already introduced yesterday during the roundtable, but I will tell you something more during this talk. So to start with the outline of the lecture, I'll start with motivations. You will hear again some common things that you have been hearing during the school, I guess. But it's important to hammer on some key points in ISM studies. And so in the first part, in the motivation, I will give my personal view of why are we interested in studying the ISM, and I will give, in particular, I will stress and highlight something that for this lecture I will call the 3M problems: multi-scale, multi-phase, and multi-tracer. And I will give you hints on how the radio wavelength band can help solve some of the questions in this complexity of interstellar medium. Then I will look in more details into radio window, some historical background, and explain to you what tools we have in hand to study radio waves in astronomy. At this point, I will break, so I will give you some time to ask questions if you have. And then I will detail, I was a bit optimistic in the abstract. ISM and radio, you will see, it's a very broad subject. So I will focus on two main mechanisms that can be probed by the radio band, in particular the H1 in galaxies and the magnetized content of galaxies. As these close magnetic fields, maybe you will have some reminiscence of last week lecture by Kate Pattle. And then we'll give you some perspectives in the radio band. Take a message: the future is bright in the radio, but challenging. And I will give you, there are several facilities that will be rated, like LOFAR, DLA. There are present facilities like NanoFAR that are coming at full run now. And then I will focus on the square kilometer array, really. Before starting, some disclaimers. I will give you my very personal and biased, possibly, view of the ISM. I work on galactic interstellar medium, so sometimes galactic will mean Milky Way ISM. Some key radio signals, I will try to mention most of them, but of course I cannot detail all of them. So in particular, molecules won't be in this lecture, but you had several lectures on this topic. Other things I won't have the time to go through are radio combination lines. They're a very powerful tool to explore the ionized gas in galaxies, pulsars as well, and some spectral properties that can be turned on in the presence of magnetic fields, like Zeeman effect for some very specific chemical species. And radio telescopes, for what concerns this talk, will be between centimeter to meter mostly, although, of course, yesterday we have been also hearing that from Javier, radio waves go up to higher frequencies, to lower wavelength, to the millimeter range. So all these, of course, I had to make choices, and but these choices are actually pointing out that the radio window has a very powerful potential to study ISM in general, but please, no hard feelings. So, and I'll try to make a lecture that can be still understandable for the newcomers. but hopefully interesting for those of you that already know much of ISM. So to start with, why are we interested in the ISM? All of you have your own answer because you're here, I guess. First and foremost, of course, ISM is where the formation of stars and planets is seated. And here I'm showing you the sun image in the UV, nothing to do with a radio, but it's a beautiful image where you also see the Earth in the background. And so if you ever wonder of formation of stars and planets, you need to understand the complexity of the interstellar medium that you have been going through during these couple of weeks. This is not just a local question on the local universe. This now is a plot showing you the star formation rate density, so the efficiency of galaxies in transforming, converting gas into stars as a function of look-back time or redshift. So present times are here on the left, past here is on the right. And this is a famous review of 10 years ago now, basically collecting data from FUV, far ultraviolet to far infrared. And the basic idea to explain these kind of trends in the ability of galaxies in the universe to form stars are connected to large-scale accretion and feedback processes on large scale in galaxies. So the general idea is that in the early universe, basically you have very little feedback acting. And so cold gas can rapidly accrete and also through mergers and form stars. Eventually, these stars will start to feedback the ambient medium and quench star formation. And so there is this kind of peak period of star formation, something called cosmic noon. But something I want to highlight from my galactic Milky Way perspective is something that the authors acknowledge in their work. And they say this trend is primarily determined by gas accretion feedback process at galactic scales. But it does miss a crucial point. In particular, the way the inner working of galaxies rooted in the physics of the interstellar medium that is key to identify the small scale mechanisms that really determine the rate of conversion of gas into stars. So these small scale mechanisms that they refer to is really what all the main people that all the lecturers here are trying to give you a flavor of. Rough approximation. Maybe you all know this from university, but the idea is that if you only account for gravity making collapsing some spherical cloud of cold gas, yesterday Javier pointed out all the multi-phase nature of the ISM. If this cloud have pressure balance, then this will collapse in freefall time that basically depend on the average density of this uniform medium. Given conditions for the Milky Way cold gas in the disk, you would end up having freefall time of a few million years and a star formation rate of about 200 to 300 solar masses per year. Now, what is in the latest estimates, here a paper, Elia and collaborators in 2022, a few years ago, based on far infrared data with the Herschel telescope, it's a couple of a few solar masses per year. So there are two orders of magnitude difference in this zero level approach in understanding how gas collapse into star formation. So it's really key. It's not a factor of a few. It's orders of magnitude. It's really key to understand what are those small scale mechanisms before. And of course, we are almost the last cool. So you know what are these mechanisms that are inhibiting star formation somehow in the ISM. But I would like to phrase them into these three M problems: multi-scale, multi-phase, and multi-tracer, as I said before. And I find this image that is a recent paper by Borleff and collaborators that put together an optical image from the Hubble Space Telescope and infrared from the Sophia telescope in the infrared. And here, basically in this single image, you have a lot of information concerning large scale, small scales, ISM complexity. Here you're seeing young star-forming regions. I don't know if you actually can see them. Let me close a bit the blinds. Yeah, so here you can see these reddish blobs tracing high mass star formation happening in the M51 galaxy, the Whirlpool galaxy. And you can also see that these star-forming regions are typically located along dark lanes that are tracing starlight extinction from interstellar dust that you heard of yesterday. And then you can see these drapery pattern tracing the plane of the sky magnetic field as traced always by dust grains in the ISM. You can also see the M51 galaxy interacting with its neighbor, pointing out to the fact that galaxies are not isolated system. So here you clearly see these multi-phase interactions at play between gas magnetic fields. And of course, here there are cosmic rays, dust grains are all essential contributors to heating and cooling process in the ISM. We'll go back to that later. But really the key point of this slide here at this point is the multi-scale nature. So those small scale processes that were mentioned before that would happen in the ISM are actually going through, you see, almost 8 orders of magnitude in physical scale, from 10 to the 4 parsec, where star formation is actually going on. And all these scales somehow are linked. And so this shows you complexity to understand how stars form out of a multi-scale system. And again, something that was told yesterday is that these, as I said before, are not isolated systems, and they're energized both at large scales and at small scales through stellar feedback that imprint, whoa, conspiracy. That imprint energy in the system through winds, supernovae, and again, as I said, cosmic rays. And all of that triggers turbulent motions in the ISM. So it's a turbulent media, and as you can clearly see, it's a magnetized turbulent media. And rule of thumb, the complexity to describe this medium is that, as Javier pointed out yesterday, in terms of energy densities, all these processes, cosmic rays, magnetic fields, turbulence, and thermal properties of the gas share the same energy density. So it's very difficult to neglect one of these mechanisms if you want to understand ISM dynamics in general. And eventually, what we want to do is understanding how we go from diffuse, the ionized gas in the ISM down how this diffuse gas condensed to cold molecular gas or cold neutral medium, what Javier was mentioning yesterday, where stars are actually forming and then producing feedback into the ambient medium. This is a nice way to show the ISM matter cycle. You have been seeing, I'm sure, many different ways of this diagram. This is a plot by Pierre Lesafre and collaborators last year, which shows the challenge of tracing gas from the hot ionized phase. Here you see the ionization fraction expected over orders of magnitude in temperatures and density. You can also see that despite the difference in temperature and densities, these are the pressure equilibrium phases in the ISM. You see this is isobaric curves here. So all in all, what I want to say here is that eventually the ISM is a continuum medium, okay? And with data, what we're doing, we are discretizing these continuum medium. And the challenge for observers is to put pieces together. And these pieces are of very different nature. They can be continuum data, and you've been hearing of dust continuum emission. You have thermal and non-thermal processes in the radio band. Thermal being, for instance, Bremsstrahlung radiation from interaction of charged particles in very ionized hot media. Non-thermal processes like synchrotron emission, I will go back into that during this talk. And all of these continuum processes can teach you about the density of the gas, its temperature, properties of cosmic rays and magnetic fields. Of course, you have spectroscopy, both emission and absorption of different chemical species from ionized gas to atomic and molecular. And from that, you can learn about the thermodynamics, kinematics, turbulent properties of the ISM, magnetic fields again, as I said before, some spectral properties like Zeeman splitting can appear in the presence of magnetic fields and you can measure it. Again, you can measure properties of cosmic rays because they, as Javier was pointing out yesterday, they trigger chemistry in very dense and cold media. You can have direct measurements, direct detections of cosmic rays, in particular with facilities both on the ground and, for instance, the International Space Station. And finally, you can use even transients to probe to probe ISM properties. You can use pulses, for instance, again, as I mentioned already yesterday, but they can allow you to measure magnetic fields through rotation measures. The signal, the impulse of pulses is dispersed into the ISM and into the ionized gas. In particular, you can measure something called dispersion measure that is directly connected with the density of ionized gas along the line of sight. And also, if you track a single pulsar in time, well, you can probe, since these are sending you pulses on very short timescales, you can also probe turbulence on a very small timescales in the ISM. So the variety of traces and processes is huge. And as I said, the challenge of observers is making sense of all these pieces and putting them together. And so where the radio comes in, well, first of all, the radio band is one of the largest band that is actually observable from Earth. And goes, as I said before, between millimeter to decameter wavelength, or in frequencies between 30 megahertz roughly to 300 gigahertz. And the point is that I really want to highlight that this 3M problem is need for the radio bands is need to address this 3M problem. Okay, so at 21 centimeter, you get access to the H1 spin flip line. I will go back into that in the lecture. But basically, it's the main probe of neutral hydrogen in the universe. And so you can trace atomic gas, for instance. You can trace ionized gas in many different ways. As I said before, through radio combination lines, through Bremsstrahlung thermal continuum, and radio combination lines, for instance, they go from centimeters to meter, depending on the temperature of the gas. You can trace different species, either hydrogen or carbon, going to longer wavelength or shorter frequencies. And then, of course, there is the whole molecular complexity that was already discussed during the goes up to the millimeter range. And in this range, as it partially was discussed yesterday, there are also very, very interesting species like complex organic molecules, for instance, at about 30 gigahertz, that are possibly tracing the original bricks of life, specific environments in dense ISM phases. So multi-phase, of course, and then multi-tracer, because through all these mechanisms, you're seeing here continuum, spectral lines. You can probe velocity field, you can probe density field, you can probe magnetic fields in very different ways through synchrotron radiation, what I call non-thermal continuum here, and I'll detail that later on. Farther rotation, I remind you what it is. And again, as I said, Zeeman splitting, that you can basically observe depending on the chemical species. But you see the main probes of Zeeman splitting that are really the, Zeeman splitting is the only almost direct way of measuring magnetic fields in the ISM. And there are several species that you can use, H1, OH, and CN. All of that is in the radio band, okay? And finally, the multiscale properties. I will show you how to combine large and small scales, but basically you can combine different techniques, observational techniques to have a multi-scale probe of all these processes, particularly combining single dish observation and radio interferometers. So now I will give you some more details about the radio window, some historical background, some details about the tools we use to study radio waves in astronomy. Early 20th century, the ionosphere was found to be a very good mirror of radio waves. That had, mostly at that time, a great potential for communication. But somehow astronomers at that time thought that such property of the ionosphere would kill radio astronomy. So they at that time, they would think that seeing radio waves from the universe would be completely impossible because of the ionosphere. And now we know that actually radio waves waves in general can propagate if the frequency of the waves is larger than some critical frequency, that is the plasma frequency of the medium, that typically depends on the density of electrons in the medium. And then for typical values in the ionosphere, this cutoff frequency is 10 megahertz. So it means that basically it's true that below 10 megahertz, we're completely blind to radio emission from the universe. But above 10 megahertz, this is possible. And just for comparison, in diffuse ISM, however, these plasma frequency in typical conditions is of the order of kilohertz. So all the radio waves that I've introduced you, we can easily detect easily. It's very complex, but we can detect them. And this is how this is why the discovery of radio waves was a serendipitous discovery, because people were not expecting to see them. But in the early 30s, Karl Jansky, that was a radio engineer working in the Bell Telescope laboratories, discovered a very periodic signal that it was coming back in the sky every night. And that eventually associated with with a point that was very close to what was considered the center of the galaxy at the time. Discovery went to the New York Times, this New York Times article, showing that radio waves from the cosmos were actually possible to detect. So now this is died. No problem. And this is the kind of system, directional antennas that Karl Jansky was using in the Bell telephone laboratories. But something I want you to focus in this article is, well, okay, the title, New Radio Waves Traced to the Center of the Milky Way. But something interesting here, it's this comment, its intensity is low. And Jansky, actually, that was an engineer, is mostly famous in astronomy for introducing new units. And you can see that one Jansky is really capturing the fact that these radio waves exist, but their intensity is low. It's 10 to the minus 26 watts per meter square per hertz. And just a note, often in terms of specific intensity, then Jansky's teradian are converting into Kelvin. as was pointed out by Javier yesterday, using the Rayleigh-Jeans approximation in the radio band. And this brightness temperature corresponds to the temperature that a black body would have emitting the same intensity of that you're detecting with your telescope. And so this is Karjansky in the 30s, drawing what he would see, this fluffy emission around the galactic center. And after not even a century, this is the image now that we have of the galactic center. See, you can see the complexity of the image. This is done with a Meerkat telescope. And here you're basically seeing the combined information, both coming from synchrotron radiation, and are most likely these huge high aspect ratio filaments are caused by non-thermal processes. And here in reddish, you see Bremsstrahlung emission. The different colors capture the spectral index of the intensity versus frequency that encodes the different physical processes, can be synchrotron, can be Bremsstrahlung, for instance. So what are the tools that we have in hand? Of course, tools are telescopes. But the point I want to make here for radio observations, well, you know that you may know that all telescopes are diffraction limited. This means that they will never be able to see an actual point source as an actual point, but they will give you an answer that depend on the technical properties of the telescope. So that you will always get for a point source some kind of diffraction pattern that will depend on that will give you the angular resolution of the telescope. And so the point spread function, the fact that the single point is actually spread over the sky, is at first order dependent on the ratio between the observational wavelength and the size of your aperture of the telescope. So why am I making this point? That could be trivial, but imagine you want to see again M51. Now we have beautiful image of M51 with James Webb Telescope in the infrared wavelength 10 to the minus 6 meter. And then you'd like to have the same, you want to combine data. Okay, so you want to have the same kind of texture and in the radio band, for instance, to trace H1, atomic hydrogen here. Or how do you do that? Well, you take, you want the same angular resolution, but now you are 21 centimeter, or there's a magnitude longer wavelength. And now the aperture of a telescope should go to 400 kilometers. So it's clearly not feasible in reality to have a single parabola with such a diameter. That is the distance basically to International Space Station from the ground. So of course, angular resolutions for radio telescopes is a limitation. Nevertheless, there is a large selection of telescopes with very large diameters from that you may have used or already saw in your studies and work. From the RM 30-meter telescope in Spain. Here you're seeing the Moyang Parkes 64-meter telescope. And then 100-meter telescope in Germany, the 300-meter telescope of Arecibo that now doesn't exist anymore because the signal just fell. And the biggest telescope, the largest telescope, single dish telescope that we have in the radio is this FAST telescope in China that is 500-meter wide. But even with such a huge infrastructure, you get to arc-minute scale at 21 centimeter. That is way worse than the few arc second you can get in the optical through amateur telescopes. So what's the way to circumvent this problem? You may, of course, know that interferometry. So the general idea of interferometry is that instead of having a single aperture, you distribute small apertures and synthesize a larger one. And so now the PSF, the angular resolution of your telescope, won't be dependent on the single aperture, but it will depend on the longest distance between two small apertures in your system. And so here you can see now a 21 centimeter with a VLA, maximum baseline of 35 kilometers. You can reach arc-second angular resolutions. And here I'm showing you the Meerkat telescope that can reach at, similar angular resolution of the order of arc-seconds. This is the same telescope that was used to produce the continuum image of the galactic center I showed you before. But of course, if you go to different frequencies, the technology changes abruptly. And here you can see the kind of antennas that are still used with the same principle, interferometry. But now you don't have single dishes anymore. You have these kind of dipole antennas. I mean, I don't know if you remember TV antennas on the roofs of houses, but they remind this kind of technology. And you can have structures like Nanophore in France with a maximum baseline of about 3 kilometers that can allow you to see arc-minute scales at meter wavelength, and LOFAR that in the Northern Hemisphere is a distributed network all around Europe and can have baselines between hundreds kilometers to thousands of kilometers. So you can reach sub-arc seconds resolution at meter wavelength. How does interferometry work? In a few words, as I said, so you replace a single aperture with multiple apertures. And the end goal is to correlate all the signal that is seen by the distinct apertures. And given a given base and given a certain baseline, basically you're sensitive to a specific angular scale in the sky. So each baseline is basically probing specific Fourier modes of your sky signal. So when you work in interferometry, it's like you're working directly in Fourier space of the sky. So what you do is you build your telescopes at different baselines and you hope to cover up the Fourier space. Then in principle, what you would need to do is to invert the Fourier transform and get the true sky. These are integrals. In reality, of course, the problems start because the Fourier space is sparsely, poorly sampled. And there will be always a problem of zero spacing. You will never be able to put two antennas really attached together. And so here, just for example, this is not a scale, but I took just an image of the M51 Galaxy. Imagine you have two antennas, and with two antennas in these UV planes, so this is your Fourier space, you have you're sampling 2 points. And if you have that, so the observed sky will look like a fringe pattern, as you can see here. So the end goal of interferometry is that you need to fill this Fourier space. So you can build more antennas, and of course this goes with a cost because you need to build more infrastructure. And with 12 antennas in this case, in single snapshot you get this image. But you can use the fact that Earth rotates. And so if you integrate over time, you're actually using the fact that you're filling in the Fourier space thanks to the Earth rotation. And then this already improves your recovery of the signal as you start seeing existing features there, specific features. And so eventually, of course, this is an idealized case, you're covering up all your Fourier space. But you see that, and you're reconstructing the true sky at a certain level. But as I said before, there's always this problem of short spacing. Remember, small baselines correspond to large angular scales, since there is the element of Fourier space, and large baselines is smaller angular scales. So you always have this problem of missing large scales. And here, just for an example, this is an actual UV plane from the Low for 2 meter sky survey. And you clearly see this hole in the center showing you missing, that you're filtering out some large scale contribution. So all in all, often when you deal with radio observations at high resolution, you may want to combine interferometric data on one hand and single dish data on the other. And so this is what has been done with the ASCAP and Parkes telescopes here. This is the ASCAP image that allows you to get access both to the small scales and to the large scales. And so at this stage, you really can probe the multi-scale properties of ISM I was mentioning before. So to wrap up these first two parts, I hope I have convinced you that radio band really can help address some key questions on the complexity of the ISM, in particular in terms of these multi-phase, multi-scale processes through different techniques. But radio observations are challenging. There are limiting angular resolutions with standard single apertures. Of course, you have interferometry, but then it is a tricky business. Imaging is not obvious to obtain. So, but through combining interferometry and single dish, then you can also access this multi-scale acts of ISM physics. So here I would stop. And if you have questions, otherwise we can keep on. And Jérôme.
What is the signal to noise ratio you achieve, for instance, in the image of the center of the galaxy at millimeter waves?
At meter
waves, right?
I don't really know on top of my head. These are very sensitive telescopes. I don't know on top of my head, but I'm sure it's almost over 10 signal to noise of 10 or so. Yeah. So you can. The point is that the sensitivity of Meerkat is such a good sensitivity that you start seeing in high details these, for instance, these non-thermal filaments and the extent of these non-thermal filaments.
Other questions? Been so good, you Chris, you understand everything about the radio.
Okay, I can go on, and then we'll see at the end. And so now I will detail a few mechanisms, physical mechanisms that can be probed with radio waves, in particular, as I said before, at the H1. And the first motivation, of course, is the atomic hydrogen is the most abundant element in the universe. And it really allows you to trace the mass reservoir of galactic systems. Here you can see this is a famous Nature paper of many years ago. But you can see the extent of the H1 in galaxies compared to the optical extent of galaxies. So through H1, you can really see that these galaxies, this is in the M81 group, the galaxies are not isolated systems, are interacting with each other. And here, this is a more modern view of the NGC 4897 galaxy. And again, you can see that compared to the optical that you can see in the back, the H1 extent here in these reddish colors is way more extended. Can go up to hundreds of kiloparsecs compared to the tens of kiloparsecs on Milky Way-like galaxies that are seen in the optical. So H1 is a great probe of where gas is accreting in galaxies, for instance. And for our own galaxy, here I'm showing you the H1 column density weighted on the respective Doppler velocity. So it's telling you already, these different colors are telling you kinematics, okay? The motion of gas. And you can see these large scale features that are connected to large scale motion around the sun. Well, actually, yeah, Milky Way, large scale Milky Way motions, okay? And also what you can see is that, well, you can also see the interaction of the Milky Way with two nearby dwarf galaxies, the Magellanic systems. But mostly what you can see is that basically you have H1 along every line of sight in the Milky Way. So for different purposes, you want to study how the diffuse medium condenses into cold and dense medium in the Milky Way, or you're interested in background sources, you need to be interested in galactic diffuse medium, because these, even at high latitude, these diffuse patchy ISM will affect any extragalactic measurements. So here we enter something that I won't detail, but we enter in the regime of foreground galactic foreground contaminations to extragalactic signals. From where this H1 spectral lines is coming from, I don't know if you already saw that, but I had to discuss this. So this is a very peculiar transition linked to the hyperfine structure of the ground state of the H1 atom that is connected to the coupling of spins between protons and electrons. You have a higher energy state where the two particles have parallel spins, and then you have a lower energy state with antiparallel configuration. And the transition from this high energy state to this low energy state will produce a photon of 21 centimeter, of 1.4 gigahertz in particular. And there are different mechanisms that can excite this transition, and that depend on the environment, particularly in cold neutral medium or mostly collisions, but even the general, in the more diffuse medium, the general background at radio wavelength can also produce these, can also excite these spin states. And this is, generally speaking, a very low probability transition. As you can see, the Einstein coefficient, and generally speaking, the excitation of this state is extremely long. So we can see it because H1 is very abundant out there. So despite these very low probabilities, we can still measure it and can allow to measure H1 from the local universe to cosmological times. And this is the kind of spectra that you get. This is for a typical for a galaxy, UGC 11707. And what I'm showing here, it's H1 spectrum, and here we as a function of velocity, relative velocity to us. So this is in terms of Doppler velocities, and here you see frequencies. So you already see, for instance, that this transition on average is not peaking at 1.4, showing large-scale kinematics. This galaxy is moving with respect to us, but given its systemic velocity that is about 900 kilometers per second, you can also see relative motions within the galaxy, and this is actually tracing rotation of the galaxy. Some of these gas in the galaxies is coming towards us, and the other bit is going away from us. So when you look at H1 spectra of external galaxies, you clearly directly have information of large-scale kinematics. You can have an idea of the amount of H1 that is present by integrating these lines. But of course, there is the challenge for extragalactic studies is that you will suffer blending of lines within resolution elements, can be spectroscopic elements or your beam, your angular resolution of the telescope. And so it's very difficult to access the small-scale processes of the H1 gas. For comparison, So this is the same spectrum as before. Here I'm showing you an H1 spectrum towards some intermediate galactic latitude portion of the sky. So it's not dense cold neutral medium, but you still see a very structured spectrum. In more dense regions, absorption could also be present. In diffuse regions, what you're seeing here is mostly the combination of different thermal properties of the diffuse gas traced by H1. And this is something that was already mentioned yesterday by Javier. But basically, in this plot, I'm showing you that the full spectrum is a combination of several broadening of lines. Some of them are very large, some of them are very thin. And the spectral broadening is really tracing this multi-phase nature of the diffuse gas from what was introduced yesterday, the warm neutral medium, to the cold neutral medium. And as it was pointed out with different diagram, these bistable medium is really connected to the cooling processes in the ISM, particularly through the C+ line in the colder medium, and the Lyman alpha cooling in the warmer phase. And these bimodality in the cooling processes produce these bimodality in stable phases in the diffuse gas, which is not only, so what I want to add to what was said yesterday, is not just molecular gas, this stuff. This can also probe cold H1 gas, cold gas as traced by H1, that can be seen in the radio. Typical temperature from tens to hundreds of Kelvin, and densities, well, you can see here, of 100 hydrogen atoms per cubic centimeter. So this is the curve that was shown yesterday, showing two stable phases in the warm and in the cold. Here you see isothermal curves, and here is pressure versus density. And these different phases correspond to different thermal broadening of the lines. This is the warmer phase is of the order of 10 kilometers or more, kilometer per second or more, and this one is the order of a few kilometers per second in your H1 spectra. So again, when you look at the galactic H1, you can start having access to this information and understand the multi-phase nature of the ISM. As an example also, I show you here the same kind of phase diagram, but from numerical simulations, these magnetohydrodynamic simulations with thermal stability, so you have some cooling and heating process included through the Ramses code made by Eleanor Sorey and collaborator in 10 years ago now. But this is general trends that is observed. You can see the density of points are around the warm phase and the cold phase, but there is a wide range of distributions of gas in the so-called unstable phase. And this is because in turbulence on one hand, but in other cases, as discussed in this paper by Benjamin Godard, also shocks can produce transition from one phase to the other. And in actual observations, we expect then to observe such variety of thermal configurations for the hydrogen gas. It's very difficult. People is trying to produce such diagrams from observations, but it's very challenging to make it. So if we only work with emission data, as I've shown you before, in the galaxy, these are actual data of H1. We can start just given the broadening, the thermal broadening, if you want, of the spectral lines, we can start decomposing the different phases, and we can study separately what's going on for the WNM phase, for the cold neutral medium phase, and this unstable, or here called lukewarm neutral medium phase. Here I'm showing the column density, different structures. Sometimes they talk to each other. and here in terms of fraction. And you can see that, for this specific field of view, although most of the volume is filled with warm neutral medium, you go up to 30% in some spots of cold neutral medium. This kind of study right now are feasible only in the Milky Way. And in the close by future, there will also be possible in these Magellanic system, the very close by galaxies to the Milky Way. But it's really the Milky Way where we can study in detail the multi-phase nature traced by the H1. That was for one single field of view. Here I'm showing you the case where what has been studied, that is the fraction of CNM all sky. So don't believe anything that is here along the galactic plane, but outside the galactic plane, you can see how the CNM can be structured. And so at this point, you have very large scale surveys available, and you can start doing multi-scale analysis of the CNM versus WNM structure in the sky. So this is for the H1, that we can some hints of what we can do by studying H1 in the radio band. And really the key point is that with H1 we can start tackling the problem of multi-phase and multi-scale. But the radio band is also giving us another perspective, that is the magnetized content of galaxies. And this is through synchronous radiation, basically, mostly. I'm sure you already saw that during the last week lecture on magnetic fields, but I will come back and give a different perspective, possibly. One of the main points is that since the discovery in the half of the 20th century of synchrotron radiation in labs, right after astronomical sources of synchrotron has been discovered. And that was a major, even at that time, making sense of the sky was a multi-wavelength effort, basically. In the same years, starlight polarization was observed. And one of the mechanisms to explain the fact that the light towards stars was indeed polarized, because light coming out from the stellar surface goes through random motions, random walks, people would not expect a net linear polarization towards stars. And so what people at the time thought is that but if we have dust grains, and you heard about that, then, and if these dust grains do not have spherical sizes, but are slightly asymmetric, they could, if they are composed of paramagnetic materials, they could interact with magnetic fields, and then magnetic fields could just imprint a net polarization. So at this time, the idea of having interstellar magnetic fields was already circulating. And having magnetic fields in the interstellar medium suggested that also we could use these magnetic fields to accelerate those cosmic rays that would be detected on Earth. Okay, and so this is particularly important in this paper by Enrico Fermi that suggests exactly this, that the cosmic particles wandering magnetic fields in the galaxy. And so you have charged particles, you have magnetic fields. Now you know that these two components would produce synchrotron, and you can make sense of those observations of the early 30s that Karl Jansky had discovered. So it's really synchronous radiation that is happening, and what it is, it's a non-thermal radiation that is produced by
charged relativistic particles spinning around magnetic field lines. Of course, most of it is coming from light particles, electrons, even positrons could produce synchronous radiation, but most of the processes that are generating these high mass stellar winds are mostly producing electrons rather than positrons. So electrons are really the main components of cosmic rays responsible for the synchrotron emission. And this is a broadband emission, this is a broadband continuum emission. And just to give you a hint of why this is the case, the synchrotron emissivity depends on, so this is the synchrotron emissivity, depends on convoluted function of the magnetic field perpendicular to the line of sight. Since these particles spin very fast around magnetic fields, the preferred configuration where you can see magnetic synchronous radiation is when the magnetic field is perpendicular to your line of sight, and then you will see the beam of the electrons pointing towards you, like a lighthouse. Sorry, if the magnetic field would point along your line of sight, the electrons would still spin around, but would emit the lighthouse in direction that you cannot observe. And then it depends on a quantity here, is this JE, that is the cosmic ray energy flux that indicates what's the distribution in energies of your cosmic rays. And so you can see that for, this is a paper from Marco Padovani and collaborators a few years ago, for different energies, the synchrotron emission that you would see would be at slightly different frequencies. So now imagine you consider a continuous distribution of energy of cosmic rays. Of course, all these contributions will add together, and you have a continuum emission across your frequency or wavelength range. Another important thing of synchronous emission is that because this emission is very well beamed, is expected to be highly polarized. Up to 70% of the total emission is expected to be linearly polarized. So in practice, what we do, we observe intensities both sensitive to the total contribution and to the linear polarization, these Stokes parameters, Q and U. All of these quantities are dependent on the integration of the emissivity along the line of sight. And just to say that if just by looking at the total intensity as a function of frequency, you can have an information on the CRE, the cosmic ray properties, because as I said before, different population of electrons would tend to emit at different frequencies. And then from polarization measurements, you can obtain basically the polarization angle that is directly connected to the projected orientation of the magnetic field in the sky. So you can have, through polarization, also an information of the magnetic field geometry. And this is also very important because this is from a review by Ralph Klessen and Simon Glover that was here at the school. Synchrotron radiation is the strongest contribution to the interstellar radiation field at very low frequency. This holds for our galaxy, but this is true in other galaxies as well. And often the radio emission of galaxies is used compared to the infrared luminosities as a tracer of star formation rate in galaxies. And here you can see this ratio is a function of redshift. There is some dependence on the mass of galaxies, but what I want to highlight here is that the radio emission from galaxies that is mostly synchrotron radiation can be probed up to very high redshift. Okay, and so it can really help studying how star formation varies across cosmic times. in the rest of the lecture, I want to focus on another aspect that is more related to the polarization, and in particular to something called depolarization. I don't know how many of you already heard of the term depolarization. Please raise your hands. Okay. Good. It's not a zero sample, but the point is that when you use polarized data, usually when you use intensity data and you don't see signal, you would just say, okay, there is not enough column density. It's not an interesting region to look at. Okay, there is not enough emissivity there that to be interested in. For polarization, this is not the case, because even though you have stuff along the line of sight, since polarizations are vectorial sum, if you want, and vectors do not sum along the line of sight as positive scalar necessary. You can add vectors such that the total norm decrease, and this is why your polarized intensity decrease. But that could be interesting properties of the ISM you can be interested, you can use to investigate what's going on. And so, as an example, you can see here, if I go from short wavelength to long wavelength, so high frequency to low frequency, from 300 gigahertz to 600 megahertz, roughly, you can see some common features in the sky in polarized intensity, but clearly at a certain point, something is going on, right? You start missing some polarized intensity features. And this is what I call depolarization. There are several mechanisms. I will mostly focus on Faraday rotation. So you may have seen such diagrams already last week, but I'm, hammering a bit on that just to remind you. What is Faraday rotation? Well, we're interested in synchrotron radiation that is highly linear polarized. So if you look towards a synchrotron source that emits polarized light, what you actually observe on Earth through your radio telescope will depend on the observational wavelength you're using. And you can actually measure a rotation of the polarization angle that will depend on a physical quantity that is called rotation measure, which is proportional to the amount of electrons, free electrons, ionized gas along the line of sight, and the magnetic field along the line of sight. So, as a matter of fact, what Faraday rotation does is affecting circular polarization differently in different sense. What I mean is, you can always decompose a linear polarization as a combination of two circular polarized radiations with opposite signs. But because of the interaction of electrons with magnetic fields in the ISM, you have a net chirality, if you want, that will affect more one sign of the circular polarization than the other. And so when the radiation goes out of the medium, it recombines again with two different circular polarizations, but one of the circular polarization rotated more than the other. And so the net linear polarization will have experience a net rotation. So you start with some linear polarization that is composed of two circular components. You go through the medium, one circular component rotates more than the other. And so when you exit, the linear polarization you can combine is, as a matter of fact, rotated. Okay, so as a matter of, the main point I want to make here is that this is a phase that you're adding to your polarized vector. Okay, it's just a phase. So imagine to take a norm of this vector. Why Faraday rotation should affect the polarized intensity? In practice, of course, nature is more complex than that simple diagram. And there are two main effects that are contributing. First, you have, in observations, you have beams. You have, your telescope is not sensitive to infinite resolution. And so, if you have variations of the Faraday rotation on the plane of the sky, averaged across your beam, you can depolarize your signal. And the second point is that the galaxy is not just a uniform medium only contributing to farther rotating background sources, but it's also synchronometers itself. And so along the line of sight, you have a complexity of structures that emit synchrotron radiation and produce Faraday rotation. Are we completely lost in this complex configuration of magnetized ionized gas? Well, in practice, there are techniques that have been introduced, in particular Faraday tomography. Who already heard of Faraday tomography or rotation measure synthesis? In principle, Kate, I think, mentioned at least, I hope. But anyways, I will walk through it because it's very fascinating. And it's a technique that was proposed in 20 years ago. But it has been possible only very recently with telescopes like LOFAR. So it's a very new technique. And the data we're using to explore this technique are new. So let me walk through it. This is something that we measure, okay? Polarized intensity as a function of wavelength, of the wavelength, so of course, a wavelength square. This is a measured quantity. And the polarized intensity is derived from the Stokes parameters. So these are actual LOFAR data towards one line of sight, okay? And you can see in the Stokes parameters these phase that rotation measure is adding to the problem. And these kind of wavy patterns that are produced by the rotation caused by rotation measure. And the general idea in these complex signals is, again, can we use some analog of Fourier transform? Here you have waves. So the general question is, can we use some analog of Fourier transform to find the principal modes that are responsible for these wavy patterns? It's like you're combining different nodes that are different waves, and you want to see what are the principal pitch that are producing these waves. And this is exactly what we do with Faraday tomography. As a matter of fact, is a Fourier transform. It's an analog to Fourier transform of the polarized intensity as a function of lambda square. And so what you do is you find this quantity that is the analog of the Fourier transform in this new space. I call it Faraday depth. This is essentially a rotation measure. It's the same quantity as a rotation measure. So basically now you have a polarized intensity as a function of the rotation measure along this specific line of sight. These are the same data, just look with different angles. Okay, here you're looking in wavelength square space. Here you're looking in rotation measure space. What's the advantage of doing that? Well, there are a few advantages. First of all, since every mode as in space, you're averaging over your full range of scales. Here, every rotation measure value here, the polarized intensity at a given rotation measure is averaging over the full range of wavelength. So you're gaining signal to noise of the square root of the number, basically of the number of frequency channels that you have in your observations. So you have a much more sensitive probe of the medium that you're looking at. And secondly, you already have direct information on physics that it would be very difficult to see here. Okay, here you see that the rotation measure is changing sign. Now, rotation measure is the integral of a density times a scalar product of the magnetic field with the line-up side vector. So it can be positive and negative depending if the magnetic field is pointing towards you or away from you. So if you go from wavelength space to rotation measure space, you already have physical information for this specific line of sight. We know that there are possibly two components along the line of sight of magneto-ionic medium, and that the average magnetic field along this line of sight is pointing towards us. Okay, So we start having physical information just looking at the data with a different angle. And now you can do this for one line of sight. You can do that across the whole sky, or at least across large portion of the sky. This is the low for 2 meter sky survey. And you can look at this data as you would look at spectroscopic data, basically. You have spectra, you have lines of sight. So as a matter of fact, now you're going through polarized intensity. There are a lot of information captured here. You have polarized intensity as a function of rotation measure. So you have synchronous radiation happening, cosmic rays, magnetic fields, and Faraday rotation ongoing. So ionized gas, magnetic fields. Last point I want to make is that the ability, so the width of those lines that I've shown you is not random, okay? It depends on your instrumental choices, okay? And in particular, since this rotation measures space is a Fourier transform of your lambda square space, the ability to distinguish feature in these rotation measure space will depend on your frequency range. The only point I want to make here is that if you change your frequencies of an order of magnitude from 100 megahertz to 1 gigahertz, you change the resolution in rotation measure of several orders of magnitude. Why this is important? Because if we go back to the multi-phase properties of the interstellar gas, it's only at, each phase would contribute for typical path length, ionization properties, and so on, to rotation measure with typical magnetic fields of 5 microgauss to a few radian per square meter. So it's really at the low frequency end where we can start probing the multi-phase structure of the ISM through low frequency polarization and Faraday tomography. So synchrotron, the radio, I've shown you H1. I've shown you that synchrotron is a probe of different processes, magnetic fields, tracing cosmic rays, but also, thanks to the low frequency end and Faraday tomography, we can probe the multi-phase nature of the ISM. Last, I want to share you why I think the future is bright but challenging, and I will really focus on the SKA. That will basically be a huge infrastructure from sensitivity between 50 megahertz up to 15 gigahertz. Okay, and so of course this is a huge, this is the main difficulty in order to give an efficient telescope that can be efficient across all these frequency range. And to be honest, it's not just one single telescope. There are 2 telescopes, SK-Low that you can see here, made of these dipole antennas, kind of Christmas trees antennas, and a high frequency end made with these single dishes that is called SK-Mid. This is, as I was mentioning yesterday, this is a long journey started early 90s, and now it's approaching completion. It's a rather expensive experiment, and funding is not finished to be asked actually to upgrade of the actual capabilities of the telescope. So what are the main challenges? First and foremost, our diplomatic challenge. This is a global infrastructure. The SK-Mid and SK-Low are physically in 2 different places. In SK-Mid will be in Australia, in South Africa, and SK-Low will be in Australia. But the functioning of the whole telescope will be possible only with the joint effort, all member states that you can see here. So you need to put all these people at the same table and discuss and find solutions. And also, there are technological construction challenges. You need to build a lot of antennas, both in mid and low, 130,000 dipoles for low, at different distance because you want to reach different angular resolutions. So you can see maximum baselines here in mid of the order of 150 kilometers and in low of the order of 100 kilometers. all these antennas will give you not only resolutions, but since there are many, you have a large collected surface area, and then you get sensitivity. And SK will be a jump in sensitivity for both in mid and low. So it will be very exciting, but there are, of course, other challenges. In the radio domain, radio interference are very important. Some of them are known, so what you just do is just flagging some frequency bands that are too bright for communication. That are too contaminated, mostly because of communication. But we start seeing unforeseen RFIs. In particular, for instance, here I'm showing you a work by the LOFOR collaboration that shows the contamination to LOFOR data from the Starlink satellites when they cross the beam of the LOFOR telescope. And the point is that you can reach the different lines here are different distance of these telescopes, but you can reach very strong contaminations. And the problem, of course, is to find contingency plans, how to deal with such interference. And so in SKO, in particular, what people is doing is trying to find solution with Starlink itself, trying to find a way to turn off and on the telescope when for instance, when the satellite are crossing the beam of the telescope. But this is all under discussion, as you can imagine. Interacting with such corporation is not an obvious task, but this is something to keep in mind. The radio sky can be highly contaminated by sources that right now we're not too aware of. Again, in order to reach this high sensitivity, it's very great for future, of course, but it comes with a price. And as I was mentioning yesterday, the SK Observatory won't be able to process and store all the data that will come from all these antennas and so on. And so this is where the observatory actually basically asks for pledging to the member countries to guarantee an infrastructure network that can accommodate both processing and archive of the data. All these centers will be spread across the world, and there will be one single gateway towards this network that will be the environment where any user will enter to do data analysis, data combination. And so regarding what we were discussing yesterday, this is very, this is very important, because imagine you want to combine the most recent surveys in the optical, in the UV, etc., with SK surveys in the radio. You will need to go through this structure. You cannot download the data yourself and work on other servers. This is the distribution roughly of where the main centers will be. South Africa, Australia, of course, where the actual distribution products of the SK data will be at the antennas place. And then you have all these centers in India, China, Japan, actually, and Europe that will be various, and Canada. Where we are, actually, the timeline is pretty strict. So you can see now here for the two telescopes, you have low and mid. They're both under construction, but the low telescope is already under commissioning. And basically all these infrastructure that will need to accommodate data at the rate of about 300 petabyte per year. Yesterday I mentioned 700, but the 700 petabyte per year is really what is expected if additional funding is found. But at this stage, this is the rate of data that is expected. And the SRCnet we need to make it ready in a couple of years when science verification will start. And science verification, it means that a community will be engaged to propose project to verify that the instrument is properly working. And so the timeline is short, and we're doing our best to reach these deadlines, but it's clearly a hard job. And the telescope will be a full run in 2034 for a low, and this is what expected, in 2036 for mid. So 10 years time, basically. So the first cycles will still have some shared risk proposal to include it there. And not to forget that something that we still need to really account for, but there are efforts within the SKO to try and understand how to contain the environmental footprint of such a large infrastructure. These were estimates made a few years ago, and there are, of course, lower estimates because only consider the contribution in CO2 equivalent of the actual telescope, but doesn't account of all the SRCnet contribution that it will be needed to account for, because without SRCnet, you cannot use SKO essentially. But this is again something different working groups are trying to make sense of. Okay, I finished a bit earlier. It's not too bad, I guess. And so my concluding remarks are the following. Well, I hope that I gave you a flavor of the possibility of using the radio band to address a few key scientific questions and problems in studying ISM, in particular in terms of the ISM being multi-phase, multi-scale, and multi-tracer. I mean, in the sense in that there are several processes at play altogether. So I gave you, I showed you how radio observations can be done, and the challenge in radio observations combining single dish data and interferometric data. And then I detailed a few mechanisms, in particular the H1 in Galaxies, and how to trace the multi-phase and magnetized ISM through synchrotron and Fourier rotation. Then I really want to conclude with this point. The future will be bright in the radio band because many facilities will be upgraded, like LOFAR, BLA, and some new facilities will come online, like SKO. But of course, there are many challenges behind the usage and make these facilities efficient for ISM studies. And I invite all of you to take part to this challenge if you're interested. Thanks.
All right, what questions do we have?
You spoke about proprietary period for ASK data. Can you elaborate?
Proprietary time?
Yes.
So this will happen here. In science verification, all data will be public right after. And here, the actual periods is not completely defined yet. They expect, well, it will it will be a year or so, and it will also depend on how many they have expectations on how many groups will apply for how many projects, PI projects will be delivered at different stages. So it will depend on the effective number of all these projects. But it's around 1 year. This is what they're discussing.
I saw there was...
And then there are KSPs, sorry. There will be PI projects. And then afterwards, there will be in cycle 3, the key science project that will...
so the key project will be only
afterwards.
a few years after the start.
Once most of the science verification that will go through, it will start here, but it will go through the first cycles where you have shared risk and so on. But science verification will really end, at least for law, for instance, in 2033. So in 2033,
and the key project will be a large fraction of the time, or which fraction? 50?
Yes.
100%?
Again, it's not completely defined yet, but they expect that before I can tell you we can find the fraction, because before KSP starts, they expect 300 PIs program to be allowed, and then after KSPs 100. So
300 per year. 300 per year.
Yes.
Okay, and if I may. And another questions that is related to the short spacing questions. You saw the importance of short spacings, but what are the plans for SK?
Yeah, so there are always, well, it really depends on the frequency, because at certain frequencies you will be able to combine with existing single dish data. Meerkat is actually showing to be very good to recover large scales, but of course, also the field of view of MID will be of minute scales. So to go larger, you will really need to combine with different telescopes. I guess Parkes for larger scales. At low frequency, it's tough. What people is in general, both in mid and low, what people also think is you can use antennas in interferometry, but you can also use single antennas. So you can cross-correlate antennas to get the high resolution, but you can also use autocorrelation to get the larger scales. At very low frequencies, what a single antenna can see, it's a very poor resolution, but it's still, it could help us having, for instance, a mean value across the sky.
Hi, great talk. I was wondering if you could go over what Faraday rotation was again.
Yeah.
It was the first time I heard of it, so I was a little.
Okay, so Kate didn't talk about Faraday rotation. Did she talk about that? Okay. Yeah. So this is, if you go to textbook, you will see such diagrams. But really, what happens is some kind of birefringent process. I don't know if you have ever looked at optical rotation. No. Okay. But the idea is the same. You need to have, so you have a linear polarization. In the radio, it will be Faraday rotation. In the optical, can be optical rotation. It's actually one of the first proxy of interaction of light and matter that has been found with optical rotation. And so basically, you have this linear polarized light that goes through a medium. Linear polarization is telling you that your electromagnetic wave is basically oscillating on a specific direction on the polarization plane. But as I said before, you can decompose your linear polarization into circular polarization with different signs, one right-handed and one left-handed. Now, if in the intervening medium there is some chiral process, for instance, with optical polarization, what happens, you can check with chirality of molecules, sugars. For instance, if there is a net chiral process within your medium, then the two circular polarizations won't be affected in the same way. One of the two will be rotated rather than the other. And so when they recombine at the end of the medium, the linear polarization that you recombine now rotated as a net rotation. Now, in optical polarization is like chirality of molecules, but in the ISM, there's the fact that electrons are charged particles with a given charge, and they spin around magnetic fields in a given direction. And so this imprints a chirality in the process that produce a net rotation of the plane. And as I said, it's just a rotation of the polarization angle. So it's as a matter of fact, and since this is some kind of birefringent process, it depends on the frequency, on the wavelength you're looking at. And it adds this phase here in the polarization angle. But in practice, it's not just changing the phase that wouldn't change the polarized intensity, the absolute, the norm of the polarized vector, because of what I said before, because you have line of sight complexity, because you have your beam, basically. You can add vectors such that your actual polarization is reduced. And this is what you would see in this plot. Okay, here you're losing a lot of polarized intensity. Here, maybe it's not obvious, but this is the Milky Way galaxy, the Milky Way, the plane of the galaxy is running in the middle, the galactic center is here. So really what's going on here is the amount of ionized gas is more important towards the inner galaxy than the outer galaxy. And so you see more the effect of depolarization due to farther rotation towards the inner galaxy than the outer galaxy. But then if you go to lower and lower frequency, you start seeing that these depolarization effects can go at higher latitudes. And what was very striking when we started looking at low-Earth data is because of farther rotation, people wouldn't, thought to see no polarized intensities at 200 megahertz. But we do see a lot of polarized intensity, and the question is from where this polarized intensity is coming from. And since we can probe this multi-phase nature of the ISM, what we're actually figuring out is that these polarized intensities seen at these low frequencies coming from not the fully ionized gas that was thought to be traced with Faraday rotation in the beginning, but from more neutral components, cold and warm neutral medium in particular. So we start finding correlations with the H1 with these polarized intensities. And so this is teaching us something on how the phases and magnetic fields interact.
I'll come to you. I was just going to ask really quick on that. Do we have an understanding of how this changes as we move to extremely metal poor environments, like less than 5% solar? Like, so we can, as we think about total evolution, do we know what we expect at the very early universe for these types of magnetized and polarized effects?
Short answer, no, I don't know. But it will depend on I guess it will strongly depend on metallicities. I don't know how, it will depend on how your cosmic ray population will change. How cosmic rays, do they mostly lose energy through synchrotron radiation, or in the early universe you have a very strong CMB, so inverse Compton can very, very, very important. But I really don't know the answer to this question. Yeah. And the point is, again, such studies, it would be very difficult to do in external galaxies. We may hope to do something like that in very close by galaxies like Magellan Clouds. But then beam averaging most likely produce complete depolarization. But space for discovery, let's say, once sensitivity increase, you never know.
Hi, thank you. Can you come back to 63? I have
Sorry?
the previous slide, please. I have a
Oh, no,
more
sorry,
technical. Yes, this one, 63.
Yeah.
It is my understanding that depolarization has to do with random transformation. So like random rotation.
It's not really, it's not necessarily that it is a random rotation. You need to have abrupt changes in the polarization. So 90 degrees, basically, if you average, if within your beam you have a 90 degrees change of the polarization angle, this would give you zero polarization. Okay. So,
if you measure both, like U and U,
yeah,
then if one is zero, the other one is on zero. Oh.
Yeah, but you can reduce the net amount of polarization. Okay, you can reach the noise basically. Here you can see both these large scale features, and then you see noise on top of it. So you can reach the noise level, of course.
So my question is about this nice spectrum.
Yes.
Which is not really spectrum.
So
yeah,
I mean, it's called Faraday spectrum. This is
yes. And so if we had no depolarization, what would be the spectra that we would observe? And another question is, when we look at your formula, it looks like you believe that the Fourier content is kind of similar. So what would look like modulus? What would look like the modulus of the short time Fourier transform? You looked at just one Fourier transform, but when I see when I look at the left,
this is not one frequency. Sorry.
Yes, but yes, this is a modulus of the Fourier transform.
Okay. Okay.
Right?
Sorry. Yeah.
But when I look at on the left, it doesn't look so constant frequency content. So what would look like a short time Fourier transform of the signal instead of just a single Fourier transform? Or if you take the Fourier transform of the beginning and the end, would it look similar?
When you
No, it's because you take the Fourier transform.
Okay. Okay. Sorry. I would question. So to answer your first question, if there is no depolarization, you get a peak where at a certain rotation measure value.
Agreed.
That corresponds to the full length of the ISM volume that is transpassed by the synchronous radiation. Okay, so you don't get multiple peaks; you just get one peak at a certain value. For the other part of the question, I'm not sure I understand the question. Sorry.
Like for instance, if you take the first half of your signal on the left and the second half,
okay. So what
would you get the same Fourier transform?
If you cut, for instance, the frequency space, what you're changing, as a matter of fact, is, as I said before, sorry. So as a matter of fact, you're changing the frequency, and so you change the ability, the width of these lines. You can change the width of the lines. You can go thinner or broader. And if you start having cuts, for instance, you have RFIs, so you need to blank some frequency ranges. Then what you get, it's like when you do interferometry and you're sparsely sampling your UV plane, you get strong side lobes. Okay, so of course if you have a very sparse sampling lambda square space, you would have very strong side lobes, and so it would be very difficult to actually see different components. And this is the reason why Faraday tomography became possible only when very broadband facilities like LOFAR started existing. Otherwise, you get very strong side. So you may get one peak, and you understand the peak is some kind of PSF, but in this space.
Yes, my question is the first peak on the middle is the one of the left, and the second, because like for the first part, it looks to be very close, like it's like the depth is equal to 0, and there's
I mean, you can see there is a larger variation. Yeah, definitely. So there is a main peak that is causing this larger variation. And then there is the second peak that is causing not the very small scale variation in lambda square, but you can see some little peaks in there. Yeah, this is what it's causing.
Thanks.
Of course, again, about Faraday depth, because it's the thing that we don't understand very well. Following up on your previous conversation with Daniel, will it be possible with SKA to do this exercise in another galaxy? Like what is required to have enough resolution in Faraday depth to do that?
The main problem with other galaxies, for me, will be beam, the beam averaging. Okay. And SKA in the low band will be orders of magnitude more sensitive than low for today, but won't have a better resolution. So low for has a better resolution, okay, than SKA. So beam averaging will be important for such studies at these low frequencies. So I don't.
So
yeah,
probably
I don't think it would be possible to go in really in extragalactic context for such studies.
Okay.
I mean, I think in the Magellanic system it would be possible, but I don't know how much farther away. Maybe in the local group we will try it, but the resolution will be comparable. You know, it's like will be like 10 arc seconds.
So is there frequency dependence on depolarization? Because if you go back to the map, you see.
Yeah, definitely. Yes.
Yeah, this one. So like, if you go to like lower frequency, then this seems to be more.
Yeah. Yeah. The frequency dependence is here. Is the fact that the phase that produce the rotational depolarization angle is frequency dependent or wavelength dependent. Okay. And this is due, you know, I was explaining before, it's due to the physical process behind this some kind of birefringent process that depends on the frequency you're looking at. It doesn't mean that at high frequency you cannot have depolarization effects, okay? Because you still, along the line of sight, you may add up polarization structures that are not coherent, and these would produce depolarization again. If along the line of sight you have, say, 2 supernova remnants, okay, with magnetic field configuration that are 90 degrees along the line of sight, with respect to each other, then summing up, you will get 0 polarization. So there are different mechanisms. This is why I said I only focus on Faraday rotation, but you can have, you know, the turbulent structure of the magnetic field itself can produce depolarization beyond considering Faraday rotation.
Thanks.
Yeah. What about the effect of the dust on this rotation of polarization? The dust, will it damp the rotation?
Why do you consider dust here? Because I mean, here you okay. There is a point that I want to make here. You're probing different frequencies, and most likely in these 4 images, you're also probing different sources. Maybe I'm getting closer too much. So here you're mostly probing dust polarization. Here you start being dominated by synchrotron polarization. I don't know if this is the question you're asking. So yeah, my point is it was just a general idea of polarized intensity in the sky. But you can see, so the main difference between these two are related to physical mechanisms. synchrotron versus dust, but you still see common features. And then once you go to lower and lower frequencies, then you're always probing polarized synchrotron radiation, but you include the effect of further rotation.
Okay. Last quick question.
Yes, thank you for the nice presentation. I have a question which is not science related, but related to the human activity you mentioned that affects the observations. Maybe I missed it, but what is the current expectation? What are the current expectations for the future? Because this activity is on the increase, and many countries are launching very small satellites or small cubes and many human activities on the increase. And is this a real threat, or are there any expectation on that side?
Everything will be really dependent on the science case, of course. But something I want to point out is, so the two telescopes in any case are built in very desertic areas. Local RFIs are known and controlled. The problem is, as I was saying before, is these unknown and new RFI sources that may come from satellites, for instance. And the problem with Starlink is not having a few satellites around. It's the amount of satellites they are flying. And so I don't have a direct answer to your question because it's everything under discussion. But it's clearly, you can have instantaneous sources of 100 Jansky in your beam. Depending what you're doing, can be awful. So I know a postdoc at the Observatoire de Paris, Xian Zhang, that is looking with NanoFar. She's looking at planetary auroras in Stokes parameters with NanoFar. And actually, the only thing she managed to detect is Starlink so far. So she has tracks of Starlink.
Thank you.
Let's thank Andrea one more time.